Hello, Gems. Every journey begins with a choice, and today we have a choice to make, either to battle out the questions that are laid in front of us or to quit and stay weak. But remember, with every question that you attempt, every question that you battle out, you will get stronger. Every pain that you have today will be your strengths tomorrow. This is a transformation that will take time, and if you join me in this journey, with every question that we attempt, it will be a step in the direction of our goal. With this series, we will be attempting about 300 questions by its end. So that will be 300 steps in the right direction. So hop on, and we begin today with question bank 5 with that thought, wherein we'll be discussing questions from the chapter of work power energy. Okay. So previously we have discussed chapters 1, 2, 3, 4. So if you have missed out on those question bank, you can surely check it out after this one. Followers of this series will know the trend. Firstly, we discussed the previous year question trends from the various topics of this chapter, and we see which topics are most favored in BITSAT, and we then attempt about 10 questions from this variety of topics, okay, just to get a grip on the topics in this chapter. Okay, so first of all, questions were asked on work done and power. So work done, FD cos theta, you are supposed to use in different scenarios. So 7 questions were being asked from there. Potential energy, and we have chain on a table problem, or springs you have. Kinetic energy, no such questions. Conservation of energy, 2 questions. Momentum 4 and collisions 4. So that is the weightage. Let's go to the questions. 1 and 2 over here. Question 1, the relationship, so it's not about you, between force and position is as shown in the figure. So the work done by the force and displacing the body from 1 centimeters to 5 centimeters. Okay, so this is force and this is the displacement, right? So basically work will be given as FDR, right? Right, so integration from the initial to the final point. So what is integration? Basically it's area under the curve, right? And area can be negative in this context, since if you see this area and this area will cancel out each other. They are same in height actually. Okay, so my drawing does not look like that. So this is also actually 20, okay, and this is 20. So in the negative direction, then we have the width same. So this and this work will cancel out each other, right? This force and displacement for this part is in the opposite direction. So we have a negative work, and here we have positive work. So they will cancel out each other, and here and they are equal, right? So they will cancel out each other, and in this case you'll see this is 10, right? 2 minus 1, that is the, so basically you have to find this area, right? So what is the length? 2 minus 1. What is the height? 0, 10 minus 0, so which is 10. Again this length is 1 and height is 10, so again 10. Okay, so basically you'll have to add this area 10 plus 10, and this will cancel. Okay, this is, of course, this is 1 into 20, 1 into minus 20. Okay, so that cancels out. So the work done is 20 ergs. Okay, it's in the unit CGS unit, right? Dian, okay, and this is centimeter. Okay, so it's in CGS unit. CGS unit energy is in ergs. Okay, let's come to this one. Here we have a mass weight mg, which is suspended by a spring. Okay, so this is mg. So we'll have a spring force k delta x. Delta x is the extension in the string, right? So we can write F is equal to k delta x, or if this is in equilibrium, right, it's suspended. So equilibrium meaning this mg is balanced by this k delta x force. Okay, now we are only considering the magnitude. It's of course k delta x with a minus sign, but that shows a restorative force. But anyways, we are concerned about the magnitude. The energy stored in the spring is u, so you can write for extension x delta x, what is the energy? Half k delta x square, right? This is the potential energy stored in the string for this extension. Okay, you are supposed to tell this value of delta x. Okay, so you have two equations. You are supposed to obtain the value of delta x in terms of u and mg, right? So first of all, here we can write delta x as mg by k, right? and from here we'll find we'll substitute delta x, we'll find k, okay, because we don't want k, so we'll obtain k and substitute resubstitute, okay. You'll see what is happening. So half k delta x, this is what we are supposed to find. We'll substitute it, so this will become squared, right? So you'll get u, and this is k square and this is k, so we'll have 1 k in the denominator, mg square on top and k in the denominator, right? We can find k, k will be half mg square by u, okay. Now you can substitute this k over here to find delta x, right? So delta x is mg by k, so mg by k is this, okay. So underneath we have mg square and this will go on top, right, denominator, and that too, the denominator of the denominator goes into the numerator, okay. So we'll have 2u in the numerator, okay. So that will, this mg will cancel and we'll have 2u by mg, which is in option A, okay. So basically you'll have to use equilibrium and the extension and then eliminate and manipulate the variable so as to obtain delta x. So those were the first two questions. Over to the next one. Question 3 and 4 over here. In question 3 we are given a force of 5 newtons. So basically I have underlined it because I was explaining it to apparently no one. I was explaining it to camera that was not recording, okay. Anyways, so here we have a force of 5 newtons applied in certain at a certain angle, and it displaces about 0.4 meters in the horizontal direction. You are supposed to tell if the gain in the kinetic energy is 1 joules, what will be the component of force. Now this gain in the kinetic energy is prompting us to use our work energy theorem, right? Gain in the kinetic energy is nothing but work done by all the forces, right? So this you can write as FD cos theta, right? Work is FD cos theta, but that F and cos theta will club together. This is the component of force, right? So this is what we are supposed to find, and D is 0.4, kinetic energy gain is 1, right? 1 joules. So this component of force, I will call it F prime. So that is 1 by 0.4. This will be around 2.5, right? 10 by 40, 10 by 4, sorry. This is 5 by 2 or 2.5, okay. So that is our answer, which is option C. Let's come to this one. Here we have a uniform chain of length some L and mass. So we have this chain which is hanging, certain amount of it is hanging, 1/3 of its length is hanging from the edge of a table. Finally you get it back to the table, okay. You pull from the side and get it back to the table such that the entire length is on the table. Now you're supposed to tell what is the work done in this process, okay. What is the work done? Now the work done will be nothing but in such type of cases when a change is pulled back to a table. This is a standard type of questions. Here you are supposed to use the change in the potential energy, sorry, okay. So that will give you the work done, okay. So first of all, we can choose a reference. So we'll choose this as our reference, wherein we'll choose potential energy to be 0. So at the table, the potential energy is 0, okay. So the final potential energy is basically 0, right? This we can write as u final minus u initial. U final is 0, so we are left with minus u initial, okay. So this is 0. We are just supposed to find the potential energy of that configuration, right? So now this amount of length 2L by 3 is on the table, okay, flat on the table. U is 0, right? MGH, height is 0, U is 0, okay. We have chosen that as reference. Now we are supposed to find potential. This will of course have potential energy, right? So what is the mass, right? MGH we need. So G is there, M and H we need, right? H will not be L by 3, we'll come to that. So first of all, let us find the mass. Mass of the entire length L of the change is suppose M. Then it is uniform. So mass of L by 3 will become M by 3, okay. So L by 3, 1/3 of the length will have 1/3 of the mass. Uniform change, and we'll assume the mass is linearly dependent on your length, okay. So that is there. Now what will be H? Now we have found M, we have G. What will be H? H will not be over here. It wouldn't be L by 3 since the mass is not concentrated over here. It will be somewhere in the between, right? Geometric center. So here it will be half of this, which will be L by 6, right? L by 3 and half of that in the center of the hanging part, so that is L by 6. Now let's compute this. So U initial, so minus of U initial, M is M by 3, so potential energy of this part we are writing G and L by 6, and that too with a minus sign because L by 6 in the downward direction, right? We'll consider those energies to be positive, this to be negative. So basically convention to get the positive sign that we want. So MGL 3 6 are 80, which is option D. Okay, so that's about question 3 and 4. I hope the camera is recording, and let's move to the next question. We have displaced a body from this coordinates origin to some 1 1 along the line y is equal to x. So by a force this, now note that this is x square j cap and y I cap, so they have written it in a way to confuse you. Okay, so the work done by the force. Now it won't be that straightforward, you'll have to integrate it. Okay, f dr. Okay, this won't give you the r vector directly. Okay, it will give you the dr vector. The dr vector will be vector b minus vector a or b minus a. So 1 minus 0 I cap, and this will be dx, okay, dr, right? So it won't be x. So basically I'm saying you won't get r vector directly, you will get dr vector since the process is done okay, from this to this, okay, displacement. So it is an integration process used over here. So this will be dy j cap. So you have dx I cap plus dy j cap. Now you have to take the dot product of this and this. So j cap with j cap. So x square, so this will give you x square dy, okay, plus y square dx, right? Y square dx, I cap with I cap, okay. Now if you see it is done along y is equal to x, you cannot directly integrate this is not x square y, okay. Don't do that mistake. You use x is equal to y, okay, over here, since the process is done along that line. So this will be x is equal to y, we can use x as y over here, so y square dy plus, again both of these are from 0 to 1, right? So x, okay, what did I do? This won't be y square, right? So this is y, so I can write it as x, right? Both are equal, x is equal to y. So here you will get y cube by 3, right, integration, and this will give you x square by 2, right? Integration of x is x square by 2, so n plus 1 upon n plus 1. So here you are supposed to substitute the limits 0 and 1. So 0 if you put, both will be 0. 1 if you put, you'll have 1 by 3 plus half, so that is, I think, 5 by 6, right, if I'm not wrong. So of course I'll be right if I'm not wrong. 3 2s are 6, 2 plus 3 5, right? So option B, 5 by 6. Okay, so simple straightforward approach. Don't do the mistake of treating this directly as r. Okay, you'll get some other answer that might not as well match with the option, so that should give you a hint. This is dr, process is done via integration, right, from 0 origin to 1 1. Okay, so that's about this question. Over to the next one. Question 6 and 7. In question 6 we are given a potential. R is the distance from the center of the field, certain field potential. A and B are positive constants. You are supposed to tell what is the stable equilibrium distance. Okay, so R naught for stable equilibrium. So stable equilibrium means there is no force, right? How do you obtain force from, so basically net force is 0. There is force, but net it cancels out. Okay, so del U by del R will give you the force, right? So this at some r is equal to r naught, okay, which is the stable equilibrium distance in our case, let us suppose. So this will be 0, okay. So basically we are supposed to take the derivative of this with respect to r and equate it to 0 for the condition. So del U by del R, r is equal to r naught. So take the derivative. So r to the power minus 2, that will be minus 2 r to the power minus 3, right? N r raised to n minus 1, okay. So that becomes, so I can keep that in denominator. So this will be 2a by r cube, Okay, I've just taken that in denominator, and this a is also there, right? Again, 1 by r, the derivative will be, you can use the same rule, it is 1 by r square, okay, minus 1 by r square. So this is the case, and you will equate this to 0. Of course, r cannot be equal to 0, this will go to infinity, so you can cancel out the r. So 2a, so this r square cancels with this, so we'll be only left with r over here and b over here. So this implies that r naught, of course this will become the r naught, we are substituting this at r naught, okay. So this implies r naught is b by 2a, okay, b by 2a. Let me check that, r naught b by 2a, 2a by b, r naught, okay, sorry, yes, while writing I'm making this mistake. So r naught is 2a by b, which is option C, right? R naught is 2a by b. So let's come to question 7. Here we are given that the kinetic energy is in the ratio, so k1 by k2 we can write as 16 by 9, okay. You will know the relation between kinetic energy and momenta, right? P square by 2m, or 2m under root 2mk is potential, sorry, momentum, right? So it is given that the momenta are same, you are supposed to tell the ratio of the masses. So m1 by m2 you are supposed to tell. Okay, so k1 I can write as p1 square by 2m, p1 p2 are equal over here, and k2 I can write as, now this in the denominator, so p2 square and 2m1, that will go 2m2, that will go in the numerator. So this is 16 9, p1 square p2 square are equal, so they will cancel out, 2 cancel out 2, so m2 by m1 is 16 by 9. Now you might click this answer correct, but it is not the correct one. You are supposed to tell the ratio of masses, right? You are given k1 by k2 is 16 is to 9. Also you are supposed to find m1 by m2, okay, not the other way around. Please keep that in mind, okay. It might not be mentioned in the question, but you are supposed to calculate it certainly, right? The ratio is given in some way, you are supposed to find the ratio in the same way, okay. Ratio of kinetic energy is k1 by k2, right? You consider it k1 by k2. Then masses, you should consider it as m1 by m2, okay. So that is the correct choice, 9 is to 16. Over to the next one. Question 8 and 9 over here. In question 8 we have an incline, a body is initially at rest over here at height h of the incline. It is frictionless and it goes down, right? So it attains some speed, it attains just enough speed to complete this vertical circle, okay. So here the diameter of the circle is capital D. You are supposed to tell what should be this height h, so that you can complete this vertical circle, right? So you should know the concept of this vertical circle, right? The motion in a vertical circle. So what is the minimum velocity that is required for it to complete a vertical circle? If you know the concept, it is under root 5gr, okay, where r is the radius, okay. We can write it as 5g d by 2, right, in terms of the diameter, whole thing under the root, right? Radius is half of the diameter. Okay, so this is the velocity that the object needs to complete a vertical circle, and we can assume and we know that this object just completes the vertical circle, right? So this should gain that much amount of velocity. What is the velocity it gains by falling height h? It is under root 2gh, right? So this velocity it gains after falling height h is under root 2gh. So basically derive it from v square is equal to g square plus 2gh. Okay, so s is displacement, right? Displacement is this, not this, right? Displacement is this, h, a is g, and u is 0. Initially it is at rest, so v is equal to under root 2gh, that is it. Or you can use energy conservation, right? mgh is half mv square, so from there also you can find v, so you'll get the same result, okay. So these two velocities should be equal, so that the gain of the velocity by falling a height h should be equal to this velocity for it to complete the circle, right? Motion in the vertical circle. So 2gh should be equal to 5gd by 2, okay. So what will happen over here? This root can cancel and g can cancel, root can cancel, and we'll have 5d by 4, right? H as 5d by 4. Okay, I've written it wrong. Okay, it should be 5d by 4. Okay, of course d, otherwise it is dimensionally incorrect, right? So 5d by 4 is the correct choice. Let's come to this one. Here we have a mass m which is moving with a velocity v, another mass 2m initially at rest. So after collision they stick together, so m and 2m are moving together with certain velocity v prime. You are supposed to find v prime. Okay, a simple question of collision or momentum conservation. So initially, so you just supposed to write initial momentum is equal to final momentum, right? So that will do. So here m, so momentum is conserved in any type of collision. So m into v, here is the momentum. Here this is at rest, so 2m into 0, so that is 0. So here we have mv on this side, initial side. Finally we have m plus 2m, both these masses are moving with velocity v prime. So this is 3m v prime. So basic math now, v and this will cancel. So v prime is v by 3. Okay, so I didn't have options for this one, but v prime v by 3 is the correct choice over here. This was not from the Fodo Club book. Okay, by the way, for this series throughout I am referring the Fodo Club book, the BITSAT 2024 question bank book. So I mentioned it in numerous videos before. So that is my resource, just to tell you up. No, I'm not promoting, it's just a handshake, an unofficial handshake to help the aspirants out. Okay, so that's about it. Question 8 and 9 done. Over to the last question for the day. And over here I'll explain you what's happening. So here we have a height of 5 meters from where a block is dropped. This curved surfaces are frictionless, whereas there is friction over here. Okay, this length is of 8 meters and block moves from here. When you release it, just release, so this is frictionless, it moves down. Here there is some friction, so there will be some loss happening over here, but then it comes and climbs up this height h prime. Okay, you are supposed to tell what if this mu is 0.5, okay, coefficient of friction. You are supposed to tell what is this h prime height that it can climb. Okay, so basic conservation of energy. So here this energy is getting converted into kinetic energy, some loss of kinetic energy that should give you a hint, and then again some that kinetic energy is converted into potential energy, gaining a height h prime. Okay, so first of all, by falling a height h, we gain a velocity of under root 2 gh, as I mentioned in the previous question. So g is 10, h is 5. So or we'll keep it in energy terms only, that is better I think for this question. So half mv square, that is what we gain, right, by falling a height h, and v square is again and there is some loss of kinetic energy. Okay, now this should give you a hint, delta ke, the first question if you remember, and then we go this with this energy. So this is the initial kinetic energy, so potential energy that was converted into kinetic energy over here, some loss of kinetic energy over this length, and that with that loss, the energy that is left at this point, you can cover a height of, you can gain a height of mgh prime. Okay, so that is the energy conservation that I'm using. So this change in kinetic energy will be given by the work energy theorem. You're right. Okay, so this is work done, right? Work done by all the forces. So here in this case, it is only the friction force. Mg is this way. If you see for this length, right? This loss is for this length. These are frictionless. Okay, so mg is in the downward direction. Force is along this. Right? Displacement is along this. Force is along the downward direction. So that is not the contributing force, right? So in this case, friction is the contributing force, right? The block is moving this way, right? Displacement is this way, and the friction force is in the opposite direction, right? So what is the friction force? Friction force, so this will give us the change or the loss in kinetic energy. So friction force is mu mg, right? Mu nu, right? And n on the horizontal surface. Normal reaction is nothing but it's balanced by mg, right? So mu mg, and the displacement is L over here, so that is there. So you just substitute this over here, substitute the values, and you'll have your answer. Or we can write this kinetic energy. instead of writing it as kinetic energy over here, we can directly write it as a potential energy over here. Okay, so let's write it that way. mgh minus this kinetic energy loss is mgh prime. This looks nice, right? So mg is g is going to cancel, so yeah, we'll keep it. H is 5 minus mu mg, that will cancel with this one, and on the other side also we have, and L is 8, right? So h prime, this mg throughout gets cancelled. So 5 minus mu into 8, mu is 0.5, so half. So half of 8 is 4, and this is h prime. So h prime is 5 minus 4, 1 meters, which is option C. Okay, 1 meters, yeah, that is the correct choice. So basic conservation of energy, some work energy theorem, and you arrive at your answer. So that's pretty much it for today's video. I hope you are you really enjoyed this video. Join in with me in this series. Get 10 questions stronger with every video that you watch. Go watch the previous videos. If you haven't already, take some steps in the direction of the goal that you want to achieve. Okay, so keep working hard and keep enjoying physics.